My name is Dr. Shegun, okay? Today, week one will be, I believe you can see my screen. We'll be talking about, just to facilitate uh, the subtopic, linear transformation. And I believe by now you familiar yourself with what we call vector space. And due to vector space, we have R2, we have R3, which also the XYZ place. And in this case, we have different cases where we're going to check and the condition that that follows them. So, for example, if you have from our course material, there are some things that are there that we need to quickly check. Take, for example, in the linear function, how do we know this particular is well defined? And it's very simple. Let's check now together. When you have f of a, comma, f of a, comma b, which is the same, or let me say, okay, plus. Remember, we are dealing with different function. Look at what is happening up here now. We can see that from here we have the real number, the R of place 2. Then let's check. We have x. Now we have f of x comma y equals to x comma y comma 0. Meaning that our f is well defined. How you can see from R2 to R3. Now, if you now have the same function in this particular volume, how do we define it? So we have f of a comma b plus c, all in big brackets. Don't forget, all in big brackets. Just manage the pencil, the pen that I'm using for the online. Yeah, we have f of here. Here we have a plus bc, comma b plus d. So I'm just trying to establish what we mean by this. They are all equals to a plus c, comma b plus d, everything comma 0. So you can see it's moved from R2 to R3. So which is the same thing as is equals to a comma b comma 0 plus c comma d comma 0. At the end of the day, we have what we call f into a comma b, then plus f into c comma d, c comma d. Yeah. For you have to put the condition a comma b into c comma d belongs, they all belongs to, it belongs to our R2. So that is the first condition we try to establish. So in that case, they all belong to our R2. Let me write it very well so that they all belong to our R2. Let's look at this. Belongs to the R2. So now let's establish the second phase that says, on the second phase, we have what we call for any alpha, trying to establish the second one, saying for any alpha, belongs to the real and the R plane, and we have A comma B that belongs to the 2. So for us to establish this, there are things we also need to follow. For example, in this case, we have F. In this case, we have our F to be, let us quickly establish them. We have it to be F of alpha A, comma B, alpha B, which is the same thing as alpha A, comma, alpha B, comma, 0. And we assume that what is common here, what is scalar here? We said alpha is the scalar where the other vector said A, comma, B, comma, 0, which means that I can establish that alpha F in brackets A, comma, B. So in this case, we have the function of F between the vector space such that the condition 1 that we and the condition 2 above are true. You and I can take for example that my alpha is a coefficient, and I hold the F of A, comma B as a variable, and I take them out. So from there, I will be able to establish that alpha, comma, I can use my alpha, I can say my alpha is a constant. And I bring the constant out and I deal with other variables. So in this case, we establish this of fact. And let us also note that the sum of 2 plane vectors is mapped under F is the sum of the image. The images under F. Then it says that we should note that. Then, excuse me, number 2 says that a line in the plane of R2, meaning a line in the plane of R2, the same R2 we are dealing with, a line in the plane of R2 is mapped under F to a line of R2. The two property and the two property I'm talking about, the Roman figure 1 and Roman figure 2 together says F is linear. A term that we now define, let's look at the definition. Our definition says the definitions for it says let's the definition. I would like to write part of it. Let's our U and the V be vector. Let U and V be vector space. Be vector space over a field. F over a field F. Then a linear function, a linear transformation, let's call it there. A linear transformation or linear operator from U to V is a function. It's a function. That is, we're talking about T such that U map to V. So in this case now, we can now establish those properties, that is, for the linear transformation one, let's call this one linear transformation one. It simply means that T in bracket U1 plus U2 is the same thing as T in bracket U1 plus T is the same thing as T in bracket of, excuse me, so we're trying to define it. So it's going to be T in bracket U1 plus T in bracket U2. T in bracket U2. For U1, comma, for U1, for U1, comma, U2, they belong to, or they are elements of capital U. So we try to establish this. I believe you have the preliminary knowledge of all this. I'm just trying to remind us some of those things that we learned in the first semester in the linear algebra 1. And for this one to be able to move forward, we need to remind ourselves all this basic, so that we also have opportunity to move with others when we'll be on the same page. So we have here, okay, for linear 2 says, if you have T into alpha U, what does it mean? So you agree with me that alpha T in bracket U alpha T in bracket U is of, we can now say for U belongs to what now? So remember, this, it cannot be U again, it will still be alpha. Remember, it's the one we are taking out of the O thing now. So it's going to be alpha. It's going to be alpha for alpha belongs to the field, capital F, and our small u belongs to capital U. So we should take note of this condition. They are very useful and we are going to use them along the line. Now remember, the condition 1 and condition 2 can be combined to give the following equivalent function or equivalent condition. For example, I can say L3 LT3 can be T into alpha 1 U1 plus alpha 2 U2, all in brackets. So, which is the same thing as, we have it as what? Alpha 1 T into U1 plus alpha 2 T into U2. But the condition there says for alpha 1, comma alpha 2 belongs to what now? F. And U1, comma U2 belongs to the capital U. What we are saying here is that the condition 1 and condition 2, they are equivalent to the least to 3. So this can easily shown as follow. If you really want to show them, I believe you still have your course material with you. If you go through your course material, you can see how we can show them. But I will quickly help some of us to understand what we are saying when it comes to this. You can consult your course material for detail. And let me just give us an hint. What we are trying to, we will show that one of the things we need to show, the RA, we will show that LT3 belongs to LT1 and it implies LT1, and LT3 also implies LT2. Now, LT3 is true for all, I believe you remember this sign, for all alpha 1, comma, alpha 2 belongs to capital F. Therefore, it is certainly true for alpha 1 and alpha 2, that is LT1 hold. Now, you can also show that LT2 is true. Consider, we all know the method of LT2. LT2 starts from where we know the LT2 says for our LT2 above that we showed the other time, we know that T of alpha U, talking about T of alpha U, so which simply means that T of alpha U plus 0.u. Remember where we are going. We know that 0 multiplied by anything is still 0. But because of what we are working on and where we are moving to, we need to bring this to the board. We know that anything raised to power 0 is 1. So that is the method we are trying to apply here, just so that we can also get to the root of the matter. Now we have this, we can now say our alpha T into U plus what represents alpha here is 0 multiplied by T of U. So we know this particular side will be 0. Let me highlight them. We know that this particular side will be 0 because of 0 multiplied by anything will also give you 0. Therefore, you agree with me that we have what we call alpha T of U. This is proving that L2 will also hold. L2 will also hold. So at this point, I would like to give you guys the activities. Please check your activities. It's for you, not for any other person. You can also show that the condition is there. Look at activities 1 in your course material. Yes, you can lay your hands on it. Check these activities. Activities 1. So which means you can check E1, you can solve it. So if you solve this one, you have idea of what we are saying. It's talking about the condition for any A so that we can also solve it. We want to prove that LT3 is also true. And for us to prove it that is true, do I need to solve it? Okay, let me quickly explain this particular aspect so that the next one will be the one you're going to solve by yourself. Is that show that the condition L1, okay, show that the condition LT1 and LT2 together imply LT3. Together imply LT3. How do we show this particular one? If you look at the solution, it says for any A1, A2 belongs to capital. So for any A1, A2 belongs to F, we know that. And we know that our U1, U2 also belongs to capital U. So at this stage, what we need to show is very simple. We know that A1 we know that A1 we know that A1 U1 belongs to capital U and A2 U2 belongs to capital U. Therefore, our LT1 will be T in bracket A1 U1 plus, or it will be A1 U1, yes, and A2 U2, which is the same thing as T of A1 U1 plus T of A2 U2, which is the same thing as I can bring it out gradually by saying my A1 into T into U1 plus A2 to T of U2. We all know that this is equivalent to LT2. We all know that it's the same thing as LT2 by LT2 rather, yes, by LT2. Thus, our LT3 is true. Thus, our LT3 is true. And let us note the two property of any linear transformation. Let us know that is what we are trying to tell us here. They are pretty simple by saying that we know from the definition that T such that U implies V, which follow from LT1, that is linear transformation 1, or linear transformation 2, or linear transformation 3. So we can also prove all these. They are very, very simple. So we are trying to lay the foundation so that by the time you are to do the activities on your own, you will not find it difficult and you will find it interesting. So we move on to what we call the LT4, another condition that says T of 0 is equals to 0. So we all know, let us see why this is true. Since T of 0 plus 0 is equals to T of 0 plus T of 0, that is by LT1. Then when you subtract it both sides to get T of 0 equals to 0. So all these things are very important. Then we can also quickly show that LT5 is the same thing as T in bracket minus U. We want to show that is the same thing as minus T of U for all U belongs to capital U. Why is this so? Well, since 0 equals to T of 0, which is the same thing as T in bracket U minus U, which is the same thing as T of U plus T of U minus plus T of U my negative plus T of U minus. Let me rewrite this aspect so that it can all be on one page. Okay. Exactly. Sorry. Okay. From here, we can also say minus U of T. So at this stage, don't forget the negative that is there. You You can't add the two together and say you have 2. So we can now continue. We have what we call, which is equal to t of minus 2 minus u equals to minus t of u. So I want this one will now lead us to another activities for us to, can you show that another activities which I want you guys to try and lay your hands on. They are very simple. They are there in your notes. This stage, you don't need to cram anything. You just have to look into the book and do it accordingly. Follow the example we are doing. Okay, we are saying you should show how LT4 and LT5 we follow LT2. How? Can you show that? So the same way I just proved the above problem. So I want you to lay your hands on it and to quickly solve it. So these are the conditions that we'll be reflecting on, we'll be reminding ourselves on. So I don't want you to miss to next class. Please make sure you tell your friends. For those of you that who don't normally come, please, I want to advise you, when it comes to algebra, you just have to be there so that they form the basic of what you are here to do. So if you want to go into coding now, for example, those of us in computer science or engineering, there's nothing you want to code without algebra. We all know the binary. We all know 0 and 1. They are all, the principles are all from algebra here. So if you want to map one to the other, look at this. When we are doing it, it's as if we are doing a child play. But no, they are very applicable when it comes to real life. Look at the way we created 0 here. We all know that 0 plus 0, but you just have to show, you have to prove it, which we've been doing. So, and I believe in the next class, we're going to have, then for us to be able to meet up with the time, we only have, I think, for facilitation, we only have 8 weeks. So for us to cover all the course material, I want to employ you to try as much as possible to finish the whole unit 1 as been described from our from the last time. Please lay your hands on it and make sure you solve some of those problems. See you guys in the next class. And don't forget, every Saturday, 9 a.m. Nigerian time, that is when we meet on the Zoom. And the same link that I sent to you will still continue to be the same link you'll be using for every time your lecturer open the platform. Then we are planning to also see how we can create different groups so that we can also help one another and to grow. I know the time might not be convenient for some, but you just have to, it pays, you have to pay the price so that all of us can enjoy at the end of the day. So my name is Dr. Segun Oke once again. You're welcome. Thanks for attending. Bye.